So, good afternoon, everyone, and thank you very much for attending this webinar. So today we have with us Dr. Yulin Zhang. He's a PDRA working in computer science, computer vision, and machine learning at Swansea University. He has his PhD from University of Kent under the supervision of Professor Jingzhao Wang. His research mainly focuses on edge computing, wireless computing, distributed learning, and multi-robot learning system. So again, thank you very much for giving lecture. Please, Yulin, you can start now. Thank you.
Yeah, thank you. Thank you for having me. Uh, s- yes, so today I'm going to, good afternoon, everyone. I'm going to introduce some of my work from the mobile edge computing part and also from some latest work from the AI scenarios. And I'm going to introduce my research through four parts. The first one, I'm going to give a brief introduction of the background and the fundamentals of mobile edge computing. And then I'm going to introduce two works about applying MEC in vehicular scenarios, and another two works about applying MEC in some artificial intelligence scenario. And finally, I'm
Hi,
going,
Yulin.
oh, yes.
Sorry to interrupt. I think
Yeah.
I can't see your screen. If anyone else can see, now, yeah, now I can see your screen.
So,
I I couldn't see your screen previously when you said, so I can
uh,
see the small bar. Yeah, I can't see your screen now. It's just a small out, the main screen is
yeah.
completely empty. Yeah,
Can you see
now,
me
yeah,
now?
now I can see. Yeah, I can see now.
Sorry.
Perfect. Thank you.
Yeah,
No, that's fine.
sorry. Yeah. So yeah, again, I'm going to introduce the background and fundamentals of MEC and introduce two works about applying MEC in vehicular scenarios and applying MEC two works about applying MEC in some AI scenarios. And finally, I'm going to talk about some open problems and conclusions. So why do we need edge computing? So nowadays we have billions of phones and the Internet of Things devices constantly generate data. And because our phone and these IoT devices has limited computation resource, and we need real-time processing for some of its tasks, then the idea of cloud computing is proposed by uh, deploying some cloud server at some remote locations which has powerful computing resources. However, when we have the cloud computing, because the users and the servers are usually far away from each other, so this will introduce some severe delay and extra transmission energy cost. For example, if we are using some cloud or web service in UK, the server connected are usually called Europe West. So in this case, the real-time processing cannot be guaranteed. And then the idea of edge computing was then proposed by deploying the edge server at the edge of the mobile access network. For example, we can deploy the server at the base station, or we can deploy the edge server at the roadside unit for so that the vehicle can connect it to the roadside unit. And we can also deploy the server in our building and some routers so that our computer and workstations can connect it to this edge server to help them to do the processing. But compared to the powerful cloud computing, the server of edge computing is usually smaller. So there will be some computation resource constraints. And at the same time, because the servers and the users are connected through various communication links, so the bandwidth is always a constraint. And as for the vehicular task, nowadays we have a lot of autonomous vehicle applications, And these applications are usually delay sensitive and computation intensive. And we also have a very complex uh, environment for the network among vehicles, servers, RSU, MT server, and pedestrians. So then I'm going to talk about the MEC and its application from the communication point of view. For example, in the upper figure here, we have a figure for the smart city. So we have a lot of vehicles, we have passengers, we have pedestrians, we have base station, RSU, and in this network environment, the vehicle can act as a server to provide uh, processing power to the passengers or other vehicles. And at the same time, the vehicle can also act as a client. So they can upload or offload their task to the server. They can choose to upload it to the RSU unit or to upload to another vehicle or to the base station so that these edge servers can help to do the processing. So we can see there will have a lot of interference among this complex network environment. And again, for the vehicle, because vehicles are always moving, and we know that when the user and service are connected, the channel is always time varying, and when the vehicle is moving, there will be delay in channel state information, and we also have Doppler split here. And although we already have the vehicle to everything communications, so the vehicle can get connected to another vehicle through dedicated allocated bandwidth for vehicle-to-vehicle links. And we also have bandwidth allocated for vehicle-to infrastructure links. And also we have vehicle-to-pedestrian link, but the bandwidth is always a limitation. And we can see that choosing the offloading decision, choose which one to be the user, which one to be the server, and which how to allocate the resource of the communication links, the bandwidth will be a problem for the from the communication point of view. And also we can think the MEC from the computation point of view. So right now we have various vehicular tasks. For example, we have age-assisted perception here. The vehicle can send its sensing data to RSU or to a base station using the edge server there to do their perception tasks. And we have the cooperative perception. For example, the vehicle will use the sensing data, the onboard sensing data, and also the sensing data from the infrastructures or other vehicles to jointly do the perception work. And this will use a lot of computation resources. And we also have the joint device edge inference here. So the vehicle and the edge will train the neural network at the same time in order to reduce the delay. And we also have the federated learning. Each vehicle can train its own model using its own data and then upload its parameters to the central server to do the parameter aggregation. And because the computation resource of the vehicle or the edge server is limited, and then we need to consider the problem of the computational limitation and considering the offloading decision, the resource management of the computation resource. And next, I want to introduce two works uh, in MEC and vehicular scenarios. The first one is latency minimization for MEC V2X assisted autonomous vehicle task offloading. So, considering the bottleneck of computation and bottleneck of communication, I introduced earlier. In this work, we want uh, to utilize the weakened computation resource from the weakened vehicle in order to solve the problem of a computation bottleneck. And at the same time, we want to reuse the frequency in the V2V links in order to solve the problem of communication bottleneck so that we don't need to add additional interference in the traditional RSU offloading. And we also want to consider the movement of vehicle so that we can have a more realistic scenario. And as shown in this figure here, in this the road is divided into several sub areas, and among each sub area, the vehicle can do the V2V communication to offload its task to another vehicle, and the frequency can be reused among these small sub areas. And when a task is coming at a vehicle, it will always have three decisions. The first one is local computation. The vehicle will use its onboard computation resource to do the computation. And the second one is RC offloading. It will upload its task to the RCU server to do the uh, RCU offloading. And the third one is assistant vehicle offloading. So the vehicle will upload its task to another vehicle to do this processing. And uh, we can see that the road can be divided into M sub-areas, and the frequency of V2V communication can be reused among N sub-areas. And the goal is to minimize the overall delay of all of these vehicles by allocating the offloading decisions, the communication, and the computation resource. And this will be a mixed integer nonlinear programming problem, which is very complex. So we try to solve this problem through two steps. The first one is to do the assistant vehicle offloading and power allocation. So we proposed a modified PSO algorithm with lower complexity and low average power consumption. And the second step is to do the RCU offloading, local computation, computing and bandwidth allocation. So we proposed an integer constraint relaxation iteration algorithm through parameter transformation and the constraints relaxation. Sorry. And here we have some simulation results. So we can see that the proposed algorithm outperforms other comparison algorithms, and we can also see that the Doppler effect will increase the transmission delay and or increase the total delay. And we can also see that different sub-area allocation schemes will have different results. So we can see that if we apply n equals to 2, which means that the frequency will be reused every two sub-areas, and this will have the lowest total delay. And we also can infer the best scheme of sub-area divisions. For example, in the figure here, when there are 24 vehicles on the road, uh, allocating 4 sub-areas will be the best scheme. And when there are 48 vehicles on the road, applying 8 sub-areas will be the best scheme. And the next is the latency minimization for MEC assisted adaptive hybrid fusion in vehicular cooperative perception. So the motivation comes from two traditional fusion schemes in cooperative perception. The first one is late fusion. So imagine we have one requesting vehicle to do the cooperative perception task, and we have the assistant vehicle and the RSU both have their own sensing data. And in the late fusion, each vehicle and RSU will do the object detection using its local data, and then they will fuse these results and do the late fusion to have the final cooperative perception result. And in the early fusion, uh, each vehicle and the RSU will send their raw sensing data to the requesting vehicle and fuse this raw sensing data and then do the object detection. And generally speaking, uh, early fusion will have higher accuracy than the late fusion, but it will require a lot of communication overhead because in this case, each vehicle and RSU will send the raw sensing data through wireless communication links. And then there is the hybrid fusion scheme, which will combine the late fusion and the early fusion to uh, to reduce the communication burden. And in this case, when the object is close to the requesting vehicle, which means the detection accuracy is usually high. And in this case, they will apply the late fusion to reduce the communication overhead. But when the object is far away from the vehicle, they will use the early fusion to improve the accuracy. And we're considering this hybrid fusion scheme, and we'll introduce the additional computing resource of MEC in these scenarios to help the vehicle to do this kind of uh, computation training processing. And then we just want to adjust the ratio of this late fusion, early local fusion, and the early ambient fusion to with the constraints of the accuracy. And by applying allocating the communication and the computation resource to formulate this latency minimization problem. Here, this figure shows the data flow of these three fusion schemes, and this figure shows the delay model of each vehicle, assistant vehicle, and the MEC. And the goal is to reduce the overall delay of all of these vehicles. So we try to solve this problem into a iteratively way. The first step is to offload the to do the offloading ratio, computation resource, and the bandwidth allocation. We transform the non-convex problem into a convex problem by making specific substitutions, and then we will have the optimal result through the Lagrange method. And the second step is to do the power allocation. So first we fix the parameters we obtained from step one, and then do the power allocation. And the overall result can be obtained by adopting step one and step two iteratively. Here are some simulation results. So the adaptive hybrid scheme is compared with two fixed ratio baseline hybrid cooperative perception schemes, and we can see that the proposed scheme can have lower total delay under different accuracy constraints. And we can also see that the number of vehicles, the bandwidth, and the computing resource of MEC will all have a have influence on the delay performance, and our proposed method outperforms all of the other comparison schemes. And we can also see that the proposed scheme can reduce the average power consumption both at the RSU and at the vehicles. Next, I'm going to talk about two research works on MEC in artificial intelligence scenario. The first one is resource management for MEC assisted multi-layered federated learning framework. So in federated learning, we require a lot of global iterations between the local devices and the central data center. And because usually this data center is far away from the devices, this will cause some transmission delay. And because the computation resource of the LOT devices is limited, we then propose this multi-layered federated learning framework. So we have different devices such as camera, UAV, radar, and these are the device layer. So they will do their local training, but at the same time, they will offload a partial of its traffic data and the local parameters to the MEC server to do the edge training, and at the same time also partial data to the cloud server to do the cloud training. So finally, the cloud server will do this aggregation, and these two figures shows the data flow of this framework and also the delay model delay of each devices and the MEC server and the cloud server. And the goal is again we want to minimize the overall delay of all of these devices. At the same time, in this multi-layer federated learning framework. So to solve this problem, first we reformulated and transformed it into a QC/QP format, and then we proposed an algorithm based on SDR method. So from the simulation result, we can see that the proposed architecture achieves more efficient training than the traditional federated learning scheme or the centralized training scheme and the cloud-assisted training schemes. And we also try to find the balance point about the ratio of computation resource at the MEC server versus the computation resource at the cloud server. So for example, we can see when there are five MEC server, the best ratio will be around 0.7. So in this case, the lowest average latency of global iterations can be achieved. And the next one is one recent work we have about the distributed hybrid optimization for multi-robot learning. So in multi-robot system, distributed optimization is a significant challenge. For example, we have this distributed neural implicit mapping, and in this case, robots collectively learn the density field of a two-dimensional environment, and both data collection and the computation are distributed across robots. And each robot can only access to its own data and collaboratively learn this deep neural network model via peer-to-peer communication. And because second-order methods can achieve faster convergence than the widely used first-order methods, we want to combine these two methods to achieve fast convergence. will maintain robust performance. And then we propose this distributed first order and second order adaptive hybrid optimization. And we also proposed an adaptive switching mechanism to achieve uh, this fast convergence and the robust performance. First, we proposed a first order based distributed ADMM method, and then we propose a second order based dual variable modified LBFGS method, and then we propose the switch criteria and the soft switch mechanism through the convergence analysis. And here are some simulation results. For example, in the first video here, this red robot only scanning a part of this map with its LiDAR beams, and at the same time, the other vehicles, other robots are scanning other parts of uh, this map. And in the second video here, this is the communication links among each vehicles. Sorry, among each robots here, and we can have the validation loss here. So we can see that the proposed scheme can achieve the lowest validation loss, and from the reconstructed result of this map, the proposed scheme can have better performance here. And again, this hybrid optimization can also be applied to other multi-robot learning scenarios. For example, we have this distributed MNIST classification, and 10 robots will collaboratively train a neural network to recognize the handwritten digits, but each robot can only access to a single digit class, and they will connect it to each other through this wheel-based connection. And from the result, we can see that the proposed algorithm can achieve faster and have a relatively high accuracy compared to the centralized training. And this distributed optimization can also be applied to the distributed reinforcement learning. So here we have three robots trying to pursue the green robot, and in this environment with fixed black uh, obstacles. And by applying our method here, we can, from the simulation results, we can see that the average episode rewards is higher than other comparison methods here. So finally, I'm going to talk about some problems about MEC and its applications in vehicular scenarios, and also from the AI scenarios. So from the problems of resource allocation in MEC system, we can see that most of these optimization problems is mixed integer nonlinear programming problem, which is NP-hard, and the solutions are usually suboptimal. For example, in the previous work, we solved the problem iteratively, and this is not the optimal solution. So we need some new algorithm for better performance. And one of them is reinforcement learning, which is very popular nowadays in the resource allocation in the MEC system. But reinforcement learning will need a very long training time, because action space is usually very large according to the optimization problem. We have so many different offloading decisions, and in some cases, we even need to consider the subcarriers in the wireless communication to do the allocations here. So this is some areas we need to study. And another problem is the ideal assumptions uh, from the communication or resource allocation part in the MEC system. Uh, the computation, the required computation resource is usually assumed to be a fixed ratio according to the data size. But in reality, different kinds of applications requires different computation resource, and the delay or accuracy requirements are different. So if we want to consider a more realistic scenario, we need to deal with these ideal assumptions. And again, because the problem is very complicated, the solution is always very complex. And from the point problems of MEC for federated learning or distributed learning, the first problem is privacy. For example, in the previous work, we want to reduce the latency in the federated learning, but in this case, the data are partially offloaded to the MEC server and the cloud server. This violates the privacy requirement in federated learning, and in distributed learning, because there is no central server or leader robots for do this aggregation or averaging. So they are only connected to each other through peer-to-peer communication. So there will always be some privacy when they're trying to send data to others. And again, we have the adversary attack and the defense problem to be studied. For example, from the learning side, the data is not always perfect, so there will be distribution problem for the training data. And also we have some malicious nodes or robot, if they trying to say send a false update or parameters to others, this will have a very bad influence on the overall performance. And from the communication side, uh, we have some jamming attack technologies. We have some hopping defense technologies. So by jointly considering the defense and attack from communication and the learning side, will also be a very important area to be studied. And we also need to consider the robust synchronization protocols. For example, in the distributed learning, we assume that the communication runs is synchronized. But in some scenarios, for example, the channel station is not perfect, or we have some jamming attack from others. In this case, the synchronized uh, assumption cannot be guaranteed. So we also need to consider scenarios about a synchronized federated learning or distributed learning. And finally, we need to consider the device heterogeneities, because we have different devices, we have different applications. So jointly considering all of these will also be some research directions about of MEC. And yeah, that's all. Thank you very much. Thank you.